So I think I see two new faces today, if I'm not mistaken. So you were here yesterday also?
Were you here yesterday? No.
No, that's and you were also new. That's so maybe I should very shortly tell what we discussed yesterday. Well, that's totally impossible, but yet I will do a try, and then I will explain the concept of linear processes. Yesterday I sometimes spoke not sufficiently loud. Please indicate when that is the case, and if my handwriting is really getting unacceptable, also say so. My handwriting was never good, but sometimes if I get in a hurry, it really gets bad. What did we do yesterday? That's important. We spoke about processes. Processes basically were drawn as some kind of box, and processes had actions. And we gave abstract letters to them, A, B, and C, and this action could be that you would, well, shake somebody's hand, receive a message in the iPhone, read something at the screen. That is what the meaning of such an action is. It could also be, if you have two components, a communication between two components. And then we could write expressions like this, A dot B dot C. If A would be, I am shaking somebody's hand, then, and B would be, my iPhone received a message, as just happened, and C would be, I'm reading the message, then this says I'm first shaking somebody's hand, then I actually received this message, and then, what was this again? I'm looking at my iPhone. This is sequential composition. We can also write with a plus a choice, and that says I'm either doing this behavior, or I'm, for instance, doing C followed by D followed by E. So this is the sequential composition, this is the choice, and it says I'm either doing that or that. If we would have data involved, then we can write processes with data, and typically we saw this. We have a process X with a parameter N, and we could, for instance, say press an up button, so, and then this parameter is increased. So this is the way we write down recursive processes, where you have this process with an up, and if you press the up button, then actually the up will happen and the parameter will be increased. And we could also have a down button, decreasing this, then decreasing is of course with minus. And then we had the condition we could write conditions in front of it. Well, the last operator, but I will not explain this again, was the sum operator, in which we could quantify over large amount of data, and that was everything we have seen yesterday to describe processes. What we also did see was the tool set, and the tool set, we started with a description in MCRL2, a description like this, and then we transformed that in label transition systems, and we could reduce these label transition systems so that we could really get insight in the label transition systems. But here in the middle, we had linear process specifications. Now, why was this useful? Because often label transition systems were far too big. So if we just would generate a label transition system out of an MCRL specification, then we would have something which sometimes is really very, very huge. And what we rather do is we translate it first to this normal form, then optimize this normal form, do all kinds of things with it. That's a topic that I will not treat, but it is in the book, and I passed the book around, so the book is somewhere here. So if you would like a look at the later chapters, then There's a whole theory about confluence. Confluence, tau confluence, can be used to sometimes reduce at this particular level the state space, such that the label transition system is exponentially smaller than what you would have gotten without such reductions, and that really helps. What is a linear process? That is now the question. And a linear process is a process of the following shape, where we have a process with a parameter, with a number of parameters actually. I write only one parameter here, but here, this could be 0 or more parameters. Then the behavior of this linear process actually says there is something more that I will write here, but we have a condition depending on D, and I will add something more later. If the condition holds, we have an action that we can do. So if the condition is valid, this action can be done, and we have this process here that we can do after the action. The action can actually have parameters. And after doing the action, we can do the process again. So this is the basic shape. And what we say is, we have a process in a particular state. If a particular condition holds, then we can do a single action, only a single action, that is important, therefore it's called a linear process. And afterwards, we have the process x again, so this variable must be equal to that variable, and we have updated parameters. Now, it can be the case that we have multiple of these summons, so that is not one single summand, but that we have multiple summonds. So we write that down very compactly. This can be very confusing by saying I have some finite index set. So this is a finite index set. And I say that I can have, well, if there are 2 elements in there, I can have 2 summons. If there are n elements in there, I have n summons. Well, n is bad because it's also the parameter of this process, but n of these summons that I can do and I can choose from. And I simply use this index I here to indicate that we have that every summand can have its unique condition, its unique action with its unique 0 or more parameters, and then its unique effect when you reach x again. There's something more, that's the sum operator. So the sum operator I showed yesterday is written like this. So n of type not. What did we have? Something like set n followed by whatever the process is afterwards. Here I have the sum operator and I write a colon indicating that I get a data type n from this domain n. Here I have an index set. I use the same sum operator, but I write the element of here because this is just a finite index set and this is just a shorthand to write a number of these pluses. So that is this. Well, we can have processes with sum operators. We want to linearize them, so it's also possible to have a sum operator here, where we select some data element EI from the data type EI, and this EI can occur in the condition, in the action, and in the effect of the next state. And I can say a little bit about termination and about, well, I never spoke about time, but all these processes can use time also. I will ignore all these extensions for the moment. A process like this is a linear process. So this is a linear process. If it has this particular shape, one action, that's the most important thing, the variable x occurring here should also occur there. And now what we are doing is, in MCRL2, we first translate every specification, including specification with parallel operators, to this particular shape. And, well, if you start to internalize this particular normal form, then you will feel that it is actually quite simple to generate a labeled transition system out of that, because this is the whole state space. And for every state where this condition holds, we have an AI transition going to this particular state, and that is the only thing we have to do. And that means that that state space generation is quite a simple, straightforward process. Let's first give an example of a particular process that is not linear. Yeah? Yeah, so this basically is the whole state space of the process. In every state D, I can, if the condition holds, then if the condition holds, I have such an AI action. And I go to the new state, and this is exactly G, I, D, EI. So, generating the state space, I take the initial state. So, if the initial state is x with D0, I basically take D0. Then I look at all the summons, so I get a number of new states, transitions, say A1, A2, A3 to new states. And I simply explore then these states, and I, keep track of which states have been explored and not, and I simply generate the labeled transition system. A very straightforward operation. And we spent huge amounts on working and programming this toolset, and there's one golden rule. All the concepts should be clear. That is why we can survive, otherwise we could not maintain it. It should be very clear and straightforward, and all the procedures that you have should be very simple in essence, because that's the only way to make a well-working toolset. So let's do two things now. I give a process which is not a linear process, and I translate that. So I have an MCRL2 process to its linear form, and you can see the difference between the two. And then I will show you some of the typical operations that we can do with tools on linear processes. And what's very nice, so in the beginning, when I started to verify processes, I was completely convinced that processes should be verified by employing parallelism, and we worked very hard, especially the sliding window protocol was tried to verify that one. It took us 14 years to verify it. Then we had a proof that was proof checkable. Lots of interesting information came out of that, but the first attempt was to employ parallelism everywhere and to calculate with parallel process and shift them from places, etc. And this was a total disaster. It didn't work at all. So at some point, I gave up, but I can still pinpoint to the very early papers that one should not read. And it turned out that even for verification, this is a golden normal form. First, I translated everything to a linear process, and there all the verifications could be done. And what I'm seeing now here, even in certain theses of certain people here in this room, are that the linear processes are becoming, reappearing everywhere because it's very convenient. Anyhow, I should speak about, let's make a simple buffer. So we have a buffer with, how shall we call it, in and out. Here we read something, and here we deliver something, and it's just a one-place buffer, so we read something, the same as the alternating bit protocol, we deliver it, and then we pick up something after that, and we deliver it again. So we have an in and an out, and that's what can be done. So what's this process? Let's call the process B of buffer. B is equal to, well, we can read something. What can we read? Well, make it spectacular, we can read real numbers. They are supported in the toolset, but if you dive deep into it, then there's quite a lot more to say about real numbers, but by and large they work. But the theory of real numbers is not but we can read a real number, and then we deliver the real number. And then afterwards, we simply behave as the buffer again. Namely, we can read again, and we can deliver again, and we read. And this is the behavior of a buffer. And it's very nice to characterize this by such a simple equation. Why is it not linear? I should step aside so that you can compare it. Yes, we have here two actions in front of the B. In the linear process, we can only use one single action. So it's not linear, and we have to invent something to make it linear. How could we make it linear? So there is a procedure to do this in general, using Greibach normal forms, but with simple examples we can see it just on the spot. So
add a temporary parameter for B.
So the suggestion is to add a temporary parameter. So what we could do, and I think this is the perfect answer, is we simply say, well, here, well, this state in some sense is the same as that state, because that is where we can do the in action. And this is the other state, so we could add a boolean, for instance. So let's take a boolean B of type bool, and we could say here B is equal to true. I use this curly is because this is equality on data types, and I use this is as equality between processes. And here we take B is equal to false. And in this way, we store into B whether we are here or there. And then we make this linear process, X, and we simply store B in the list of parameters. So we add a parameter B. And now there are two possibilities. Namely, we can be in this state or we can be in that state. If we are in this state, when B is equal to true, actually if we get to the data types, this expression is equal to B. So we could as well write just B. Then we can do an in R action. But this in R has the sum operator in front of it. In R, and then we end up at this particular state. And here, of course, B is false, so we get X false. And I leave this space open because we also have to, well, if you are going from this state, you read the R, then at this particular state you have to recall this R. So we also have to recall R, going from that state to that state, so we have to add it to the parameter list. And this R that we read here, well, yesterday somebody complained about the fact that I used, that this R should not be R, but it is locally bound, so let's give this another name, let's call it R prime or something like that. R prime is the value that we read, and then actually it's the new parameter, we store it here such that we can use this R prime to deliver. And now, well, I add a second summand. well, in concrete cases, I never use this shorthand notation, but I just write down all the summands below each other. The second summand actually can be done if b is equal to false. So b is false or not b. That's equivalent. Then I can do the out. This parameter r here is actually the parameter r prime that I put in this place here, and so we can use r because we have now stored it. And then we end up here, and here we again have the situation, because this state is essentially this state where x, where the Boolean b is equal to true. And yeah, what should we do? Well, at this point we do not have to know anything about this r, but we can just keep it there. It turns out that if you really want to generate compact state spaces, then this r could be better be set to a default value. So maybe we simply set it to 0. Because we will not use it anyhow, and if we leave r there, then the state space will be bigger than necessary.
I think you're blocking the view from here.
Then oh. This whole process here is actually completely equivalent to this process, except that this process is linear and this process is not. And now you can see the difference between a nonlinear process. It's often more compact and easier to understand. But in this particular process, we have the state space encoded in the parameters here. And this process's linear shape is much more convenient if it comes to all kinds of manipulations, both with tools and also theoretical. What I will not be able to show you in detail, but I hope that I find time to give you an impression, is that we are capable of proving, also by hand, using the principle RSP, that these two processes are exactly equivalent. So using axioms and RSP, we can simply calculate this, and if you would be a student, then a typical exercise at the exam is give the proof of this. I will not ask you this in this particular case. Okay, so this is the linear process which plays such an important role, and I will now show you, if that is allowed, I will now show you one application of where it's extremely useful. Oh. And I do this by example. So suppose I have the following process. Let's call, so the name of this variable is not so important, that we use x, but I generally use x or p for linear processes, as long as this name is the same as the name appearing at the right. But suppose I have the following linear process, where we have a natural number, and let's model a counter being able to do up. After which we have the behavior of x, and we increase the counter. But this is my total behavior. Why is this a very problematic process if it comes to state space generation? Okay, so we have this particular process. Suppose we want to generate a state space from x0, so let's start with x0. And we have x0 here. Why is this problematic if we would ask the tool to generate the whole state space? So, infinite index, oh sorry, yeah. Yeah, so what we will see is that we have x0, and then we go to x1 with one up action, and then we go to x2 with an up action, and this goes on indefinitely, so we end up in the situation, well, we do not end up, we just simply have a far too big state space. Now, this is actually not so much a problem, because what we can see is that this n here is not fundamentally being used in this process at all. It does not appear in a condition, it does not indirectly appear in a condition, it does not influence the behavior. So, what we can do, we have actually a tool to do that. It's, all these tools working on LPSs are called LPS parallel. So LPS parallel, one of the tools that you could try, and it will simply try and find parameters that do not influence the behavior. And it will actually find that this does not influence the behavior and this does not influence the behavior. And it automatically removes such parameters. And then we get this linear equation. And now you can see the state space generation is quite straightforward, because we simply have this process X doing a loop with an up action to itself, and it is totally trivial. These kinds of, this is a very simple operation on linear processors. There are many more, but these kinds of simplifications can help us to reduce the state space. And sometimes it is not applicable by itself immediately, but if it's not applicable by itself immediately, sometimes we hide and transform the process a little bit, such that all of a sudden data parameters are not applicable. So a typical application is the following. We have a data transfer protocol. We want to prove that it is deadlock free for all the data. So we hide the delivery of the data, and then it will, using LPS parallel, remove all data parameters, making the possibly infinite state space just finite and often very small, and we can do the deadlock analysis of this particular process easily. So you can even employ this to get infinite state spaces finite and do the reductions. Anyhow, most important thing to remember is there are linear processes. This was the shape, the one part's dropped off, and they are very convenient in this particular process. This was my 15 minutes.
And it took 25 minutes, I guess, or even more.
Okay, sorry.
That's okay. So,
unless there are questions.
Yeah. I think it's
Okay.
good to ask questions if there are any. We are not in a hurry. So. Good. So, is it okay? Shall I start? Is it okay back there? Good. I should connect this one. Yeah, perfect. So I will talk about parallel processes. The presentation might be a bit dry, so every now and then if you have any questions or if you would like to work on an example, just let me know and we will engage in a discussion, right? The motivation comes from the same example that I showed you to motivate the behavioral equivalences. You remember this specification and implementation. This was the specification of a two-place FIFO, right? So there was a two-place FIFO which was supposed to take two inputs and then produce them in the same order as output, right? And then you implemented that as two one-place FIFOs, right? You remember that from the behavioral equivalences yesterday? So the idea is to put two one-place FIFOs in parallel, let them communicate internally, and then the outermost behavior, the interface behavior, should be behaviorally equivalent, for example, bisimilar, to the behavior of a two-place FIFO, okay? And in order to achieve this, you need an operator that allows to put these two in parallel, and that's the parallel composition that I will introduce next, okay? So you have seen so far actions, sequential composition, termination, plus, and this is a new operator that you will see right now. And this is denoted by two vertical bars. So P in parallel with Q means that, first of all, the two components can evolve independently from each other, okay? So if P can do an action A and evolve into P prime, so can P in parallel with Q, and it will evolve into P prime in parallel with Q, okay? So basically that denotes the interleaving of the two sides of the parallel composition. They can evolve independently of one another, and as we'll see, this will lead to a nice diamond structure, right? So that's very typical of parallel processes. Then what allows for communication is very peculiar. It's very peculiar to MCL2. It's slightly different in other process algebras, other formalisms. Namely, if P can do an alpha and evolve into P prime, and Q can do a beta and evolve into Q prime, then they can together do a multi-action denoted by alpha single vertical bar beta. So this is a multi-action, two actions happening at the same time. And then they will evolve into P prime in parallel with Q prime. Right? So these are the three rules that basically specify how a parallel composition behaves. Let's look at an example. So assume that we have A dot A in parallel with B dot B. So the order of the precedence of operator is like this. You first put a parenthesis over sequential composition, so that binds the strongest, and then parallel composition. Right? Now, first of all, the two sides can evolve independently. That is, for example, denoted by first doing an A on one side, and then doing a B on the other side, and then doing an A and a B. Or doing two A's in a row and two B's in a row. Right? So this outermost diamond structure comes from the interleaving of the two sides. Is this clear? So you can do A's and B's in any arbitrary order, as long as the order of the sequential processes that are composed are preserved. Right? Any questions about that? Is this clear? Yes? Now, because of the communication, you can also do A and B's at the same time. So, for example, here you can do an A, here you can do a B, thus you can do an A and a B at the same time and thereby arrive here. And then you can do another A and B at the same time and arrive there. And then you terminate. Right? So you can interleave the two sides, or you can do multi-actions and then synchronize, basically. Right? We cannot yet enforce synchronization, so we cannot say, for example, A and B should shake hands, right? That we cannot yet specify. That comes next. They are allowed to shake hands. They are allowed to interleave as they will. And then later on, we'll introduce another operator that forces the two sides to shake hands and basically go in lockstep. Always do communication. Right? So let's look at an example. And this gets a little bit theoretical. I will go quickly through it. This is a guy, former PhD student of Robin Milner. We heard about Robin Milner yesterday. So this is Farron Muller, and he's still, I think, working at Swansea. Yeah, and he was given this problem as his PhD thesis, basically, by Robin Milner. So the question is whether these two processes, you know the semantics of plus, you know the semantics of parallel composition, whether these two processes should be considered bisimilar or not. Right? So you could even start drawing the state space if you want. Right? You know the semantics, so you should be able to draw the state space. Do you think these two processes should be considered strongly bisimilar or not? Let's spend a minute on this. Does anyone know any answer? Does anyone have formed an opinion? Who thinks they are bisimilar? Who thinks they are not? Okay, quite a few. They are or they are not? They can be not. Yeah, probably, yeah. So some people think they are not bisimilar. Who hasn't spoken yet? Not always. Let's see. Why do you think they are not bisimilar back there? You don't know? Okay. Why do you think they are not bisimilar? Yeah, I think you rose your hand, yeah?
Formally, I can say that in the left part, we can delay the choice.
Perfect.
But in the right part, we must first resolve the choice and then...
That's very good. That's very good. So suppose you go to lunch today, and they have two sandwiches. They have kuku sabzi and they have, I don't know, roast beef as yesterday, right? If you are given, if the restaurant is serving the lunch as this process, so you can take your Coke and then later on decide whether you want to take a kuku sabzi or roast beef sandwich, right? However, if the restaurant works like this. At the moment that you choose Coke, so you can go for the Coke, but then you're caught by the restaurant and said, now you have gone for this Coke, because the Coke is packed in the same package as the sandwich. So you should go for Kukusabzi. You cannot wait later on and change your mind. Is this clear? So by the first Coke action over here, you also determine which dish you are going to get. Is this clear? So basically, the state space of this one, I can draw it so to make it clearer. So the state space of your right-hand side looks like this. As soon as you do a Coke, this is the initial state. As soon as there are two outgoing Coke actions, one on this side, one on the other side, then you're kind of doomed. You have to go for dish 1 or dish 2. Of course, there is more. There are more transitions, so you could go for dish 1 or dish 2 right away. But if you go for a Coke, then the choice for dish 1 and dish 2 is determined, right? And of course, it has a diamond structure, right? So dish 2 here, right? So dish 2, and then Coke is one diamond. Sorry. And then dish 1 and Coke is the other diamond. And then there is this multi-action going in the middle, right? So there is one state here that denotes the multi-action of Coke and dish 1, if you pick them at the same time, right? However, on this side, if you do a Coke, so you can do a Coke first, and then you have a choice between dish 1 and dish 2, right? Well, basically, then you're done, right? So these two are not bisimilar because the left-hand side offers much more choice. Basically, you can delay the choice as our colleague just noted. While this one, if you go for a Coke, then you also have chosen already for the dish. Is this clear? Shall we move on? So this was the main reason why Farrell Muller could show that parallel composition cannot be axiomatized by a finite set of rules. So you cannot write a finite set of equations that describes all the equivalences that concern parallel processes. You need either you need an infinite number of equations, that's what Milner did originally, so he wrote an infinite set of laws for parallel composition, or what the Dutch people did, so parallel composition cannot be axiomatized by a finite number of equations. And we will talk about equations tomorrow, I guess, right? I will try to jump over equations as much as I can. But that's why these two people, Jan Bergstra and Jan Willem Klop, both are alive, both are retired. They came up with an idea that you could axiomatize parallel composition using two auxiliary operators. We will not go into the details because we don't have time. But maybe tomorrow we will spend some time on equations that do axiomatize parallel composition using just these two extra auxiliary operators. But that's maybe a technical, theoretical detail that we don't want to talk about today. But it's a very fundamental result in process algebra that, first of all, this type of equation does not hold with bisimulation. That's a very important insight. And secondly, that's the fundamental reason why you need auxiliary operators or an infinite number of axioms to axiomatize parallel composition. Okay? I park the axiomatization story here. Maybe tomorrow we'll come back to it. Okay? So that's all you need to know about parallel composition in order to specify practical processes. So what you could do now, you could have two processes denoting one place FIFO and then put them in parallel. But what will happen then? This one may read from the environment. This one may also read from the environment, right? They may do all sorts of input and output action on their own. And in some cases, they may synchronize on doing an input on one side and doing an output on the other side. But in some other cases, they will just read arbitrary values from the environment without communicating, right? So another operator that we need is to specify how they can communicate. And also we need an operator that forces them to communicate as far as this connection is concerned. So they should talk on this line. And then this one should be free to input. This one should be free to output. Right? This one should not be able to read input from the environment, but it should rather synchronize with the other one's output. These are the two operators that we add to the language to enforce synchronization, basically. In some other process algebras, like Milner's CCS, this is kind of coded into the language, so you have less freedom, but the language may be slightly simpler than what we present here. Okay? Any questions so far? So the syntax for this one is as follows. Suppose you want a process that can read an arbitrary value. You write it like this. You just saw it in Jan Friso's presentation, right? So you have a process that is ready to read an arbitrary natural number, I, and then you want to tell the other side, so the other side could be a user that can only press one button, or maybe if you want, you can specify a user that can press 2 buttons or 3 buttons, whatever. The other side is able to press a button with a particular value, and then you want this side to receive exactly that value, right? Now if you look at the current structure of send 1 in parallel with receive I, it looks very chaotic. So if you draw the state space of send 1 receive I, it can do a send 1, it can do a receive 1, and then you form a diamond here. But it can also, for example, do a receive 2. Well, no one has sent value 2 to this process, right? And then it can send 1 afterwards. There are all sorts of diamonds with all sorts of values here, right? There is no way that you enforce them to talk on the same value, right? Is this clear? Now, in order to define that they should synchronize on send and receive, you add this communication operator that gives a new name to multi-action. So it says, once you do a send and receive at the same time, I call it a communication, okay? And then later on, I say if these two processes talk to each other, if they are put in parallel, then only communication is allowed, and individual send and receive should not be allowed. This enforces the whole process to only behave like this. So you remove individual communications, you have the multi-action, and by renaming, you rename that to com1. And this will be the only allowed action for the parallel composition. Right? So first off, what we do, we give a new name to the multi-action that results from send and receive with the same data parameter. Okay? So if send and receive happen with the same data parameter in a multi-action, then we give it a new name called com. And then there are axioms for it. I don't take the axioms right now. And then later, I add another outermost operator that says, for this process, only com is allowed. Nothing else is allowed. Okay? Thereby, I do not allow individual sends and receives. And in particular, I do not allow receive 2 if send 1 happened, right? If send 1 has happened, receive 2 should not be allowed. So by renaming send and receive with the same parameter to com, and then only allowing for com to happen, I get this as the outcome of the parallel process. Is this clear? Shall we do an example? Yeah? Let's do an example. What example shall I pick? Okay, so assume I have a parallel composition of two processes. I would like to mimic more or less the behavior of these two one-place FIFOs, okay? One FIFOs. So one of them is FIFO number 1. The other one is FIFO number 2. This one has out 2 action, in 2 action I. This one has out 1 action, J, and in 1 action, J. So it can read from the environment with action in 1. It should write to the common channel with action out 1. This will read from the common channel with action in 2. And it will write to the environment with action out 2. So this is how the whole behavior should look like. I should draw my box like that. Yes, that's the idea. Maybe my handwriting is not legible, so I will draw it again here. I have a one-place FIFO here. In the process. No, I wrote it intentionally like this. So this should be, oh, sorry. 1, and the other should be 2. So here I have in 1 J, out 1 J, in 2 I, out 2 I, and the input-output behavior of this whole thing is like that. So I only allow in 1 to happen with the environment and out 2 to happen with the environment, right? Now I started with this that can read from the environment value 2. It will be able to write on its channel value 2 on the common channel. And then this is ready to read any arbitrary value from the common channel, and it will reproduce the same value at the output. Okay, maybe the order is a little bit strange. Is the idea clear? So how does the state space of this one look like? Does anyone want to draw the state space? Do you want to do that? No? Anyone volunteering? Oh, you know. No? No one volunteers? So what can happen, for example? I could start, for example, reading value 1 into 1 on this side. And on the other side, I can do in 1, 2, right? They form a diamond. And then I can produce, again, diamonds with outs, right? So out 2, 1, out 1, 2, right? This is the initial state. Out 2. And then there is a multi-action that combines these two at the same time, right? This is just part of the state space. For each arbitrary I, you get one copy of this diamond, basically. Is this clear?
Can we allow those transitions except reflection?
Can we allow, oops, what happened? Can we, what was the question?
Those transitions except multi-action.
Yeah, so what we will do in the end is to put the box around here, which would allow this and this to happen. So the allow operator, the outermost allow operator, eventually will allow this and that to happen, and the rest should be basically hidden somehow. The rest should not be allowed.
But we should disallow multi-action.
Right. But before we disallow the multi-action, we actually rename it into something else and allow that instead. Right? That we'll do next. But this is not very intuitive, right? So it has read from the environment value 2, right? And then value 1 has been, well, let me see. Sorry?
Why we cannot do in and 2 out
Why can't you do? Yeah, you can. That's also there. Yes, you're right. So there is another diamond going with those.
I think the actual statement is
Much bigger. Yeah, sure.
before you apply a special communication operator and allow.
Right. This is only one scenario, but there are all sorts of diamonds all around this. Yes, sure. Correct. But I would like to note that this is a counterintuitive behavior because, in particular, it allows you to read from the environment value 2, and in the end, produce here, right? Let me see. It reads value 2, and then communicate internally value 1, and then in the end produces output 2, right? So there is this internal communication that is happening on the wrong value, basically, right? So in order to prevent that, the first thing we do, we add around this process the communication operator that says if you have receive, in this case we have out 1, and in 2, out 1, multi-action with in 2, we should give it a name, for example, communication, or say C12. Huh? This will say these type of diamonds are not allowed because they talk on the wrong data type, on the wrong data values. So these two data values do not match. Right? This type of diamond is not allowed. Basically, what should happen is that in 1, in 2, one, out, 1, 1 will be renamed into C1, 2, 1. Right. So if they communicate on different values, they will not be, this operator will not be able to rename them to C1, 2. They will remain as interleaving and then as basically individual actions in your state space. Is this clear? Right. So this enforces out 1 and in 2 on the same value to be renamed into a new action. Right. And then, as an outermost operator, I say only in 1, out 2, and C1, 2 is allowed. In 1 from the environment, out 2 to the environment, and C1, 2 as the communication between the two is allowed. Right? So this will basically say if the value that you're producing here is the same as the value that you're receiving there, you will rename it into C1, 2. That is allowed. But if you're reading a different value, for example, from the environment, that is not allowed because that's not one of these 3 actions. Yes? Does that make sense? Kind of. But what you could do afterwards, I mean in the afternoon, is to specify some simple processes based on your own example, try it out and see how the state space looks like using the tool. It's much easier to look at it at the tool than draw it on the board. And then I think you get a better feeling about this. OK, this is good enough to specify the 2-place FIFO, but we have this action C1, 2, which is not interesting from the outside world, right? C1, 2 is just an internal communication happening between the two 1-place FIFOs. And this is not interesting from the outside world, right? So the next step is to hide this. Oops. Using an operator called hide, which specifies that com is something that is not interesting from the outside world's viewpoint. So what will happen is that this operator will rename C1, 2 if you put hide of C1, 2 here into an action tau. Okay? And then if you apply branching bisimulation reduction on the whole process, then you will get basically the input-output behavior that you expect. So you will get in 1, 2, followed by out 2, 2. And that's the only behavior that you get after branching bisimulation reduction. So you basically first rename this into C1, 2. Then you allow only C1, 2 to happen as a multi-action, as the result of the multi-action, and then you rename it into tau, so you abstract from it, and then thereby you obtain the original specification. Something that is branching bisimilar to the original specification. Okay? So what we could do, I suggest I do one more example. I don't think this is yet clear. I see some people are still confused. Okay, so I spent 5 more minutes doing one more example, and then we park it here. Okay? So let's do a simpler example. We have A dot B in parallel with C dot D. Please, someone draws the state space of this one at least. Could you do that? Could you? No? Could you do that?
We can first, either we can take A
Mm-hmm.
or C.
Perfect.
Here we can take B,
Hmm.
here C. Here we have C, go D, A. B here, we
So
can go.
after AC and CA, you get at the same point again.
Yeah. So you always have a diamond, right? If you do AC or CA, you should always get to the same point. You always get a diamond structure, right? So you should close the diamond. Yep. The same for this other side, right?
AB to C.
And then close the diamond from the other side.
Here.
No, I mean, you always close the diamond every time you yeah. Mhm. And what should the label be?
Must be B.
Yeah, exactly. You can see it also from the parallel, right? It always has the same label. Right. We are not yet done because you should close the diamond also completely over there, right? So you can do AB here, CD there, so you should be able to close the diamond, outermost diamond, right?
A, B, C, D. I must put the communication.
Sure, that also, yeah. A, B, A, C, D, A, C, D, yes. And also one there. Very good. Now, thank you. Everyone agrees with this? Now let's put a communication operator around this. So we rename B in parallel with C, for example, to BE. Okay? So B multi-action C will get a new name. Someone volunteers to now make changes to this one to reflect the semantics of this. B multi-action with C becomes E. How do we change the figure? Would you like to do this? And the sponge is over there. You can. Maybe don't change that. Just cross out something if that's simpler.
There is not any erasing.
Exactly. Mm-hmm. And there should be one more or not? BC. There is no other BC. Okay. Yeah, if there is none, then there is none. You're done.
It's just rename.
It's just renaming. That's perfect. Everyone agrees with this? Then, oops. We allow A, E, and D to happen. Who volunteers to apply this one? Do you want to do that? Harry can try. You could just cross out everything that should be removed, okay? By just crossing it out using the red. So I only allow A, E, and D to happen. Right. That should remain, right? A, E, and D should remain, right? So this one should remain, right? No, there is no tau yet. So it is saying A, E, and D are allowed, the rest is not allowed. So basically you should remove a lot of transitions, right? So what should be removed, for example, here?
B, where we have B.
B should be removed, exactly. That's very good. So maybe you can cross it out.
Yes, this one,
Hmm?
and this one.
Hmm?
Nothing more.
Well, there is also C that is not allowed, so you should also remove C's. Right, and then the multi-actions that involves A, C.
Is there any contradiction between allowing A and disallowing C, or multi-action AC?
No, so basically you are not allowing multi-action AC either.
Why?
Because C is not allowed here. If you want to allow multi-action, then you should rename it into something new and then allow it here.
What A?
Maybe it's best if I show you the axioms then. But let's first finish this and then we'll go back to that, okay?
And it should be removed or not? A
AC should also be removed, that's good, yeah.
and A and D. Also. Let's finish that.
This is finished. Yes, that's good. So basically, everyone agrees with these things that are removed here? Thank you. So, I will. Yeah, I will erase those parts that are removed. Okay, so this is removed because B is not allowed individually, right? This is removed because C is not allowed individually. This is removed because B is not allowed individually. This is also removed because B was not allowed. This is removed. This is removed. This is removed. This is removed because C was not allowed individually. This is, no, this is not removed. Oh. Let me see. This was B in parallel with C, so this is C only, right? So this is removed. And let me rename this also into E so that we don't make the mistake I was making. So this is actually a new E, right? And you notice something. There is diamond that is not reachable from the initial state. So this could also be removed, right? This part is not reachable anymore because it was only reachable with a B transition. The B transition is now removed. So this part is not reachable anymore. Everyone agrees? Do you agree? This part is not reachable, so it can be removed. It was only reachable with a B transition. So this is the outcome. That's fine. This is the outcome of allowing A, E, and D after renaming with B multi-action C to E. You can only do an A, followed by an E, followed by a D. This is basically the same 2-1 place FIFOs. I renamed in one, out to, into, out to, into A, B, C, and D, basically. So I enforce them to talk on the common channel, basically. Right? So you can read an A, you are forced to talk on the common channel, and then you produce the output. Now, one more step. You could hide action E, because E is something internal to these two. And then what would happen? What would happen? So first off, this is renamed into a tau. Right? That's also a renaming action. It does not change the semantics. But then you could use LPS convert, LTS convert, right? LTS convert. LTS convert. In the tool set, to reduce this, to minimize this modulo branching by assimilation, and then you obtain exactly what you said, right? So you read an A, you write a D, basically. Is this clear? No? Good. So getting back to your question, you asked what happens to the individual actions, right? So basically, the axioms of allow, and we will do that more thoroughly in the remainder, only talk about actions being in the set or not, right? In particular, the multi-action, if it's not mentioned here, then it will be crossed out, right? So just to emphasize my point, you do not look at the components of the multi-action, you look at the multi-action as a whole. If it's not renamed into something that is allowed, it will be crossed out.
This calls then the high E.
Am I right?
When high T, essentially C was denied.
Yes.
But implicitly you can see actions in top.
Right. So this is the result of a multi-action that originally comprised of a C. Comprised of C, yeah. Consisted of a C. Yeah, you're right. Any further question? So I think we can now take a break of about 20 minutes. So we reconvene at 11 o'clock, right? And what was the next topic? Okay, yeah, we'll talk about abstract data types then. If there are any further questions about parallel processes, please do come back to me.